Hello, everyone. There's not a lot of everyone so far, but we'll get there. So I'm just going to wait just a few minutes for people to get the new link and get signed on to this one. I don't know why we've been having all this trouble lately. I didn't change anything from the last video, and it just didn't want to give me a preview. So let me know, for the people who are in the channel, type something in the chat box there when you can actually see me and hear me, so I know that it is coming through. I know you're on a slight delay from me. Okay, great, thank you. All right, so I'm just going to wait another minute or two here to give more people a chance to show up. Yeah, I don't know what the problem was. Professor Darden said that the link that I provided yesterday just wasn't working well for him, and then he created a brand new recording and it worked fine. But he just told me that just now when I told him that it wasn't working for me. So I don't know what it was with that. The link that we created for yesterday's lecture, it has, as far as I can see, all the same settings, but it just didn't want to record. And he was thinking, well, maybe YouTube has got so many people using it now that they're overloaded, but after I created a new recording, it worked fine. And for me, it looks good also because in the YouTube recording window where I can see that I have a good stream and everything else, I can actually see the chat in the same window. Last time the chat got disabled and it couldn't connect to the chat, and of course I didn't want to refresh the page once the recording was started. So you'd think, being computer scientists, we'd be a little bit better at this, but I am new at live streaming. Okay, so let's start talking about minimum spanning trees today. So we've got a graph here of the US with some sort of connections between locations. Here's a better picture, more zoomed in, of some data centers. And these are hubs where large fiber optic bundles come together and go out to other locations. So let's say that we developed a new fiber optic technology faster than anything else, but it requires us to lay some new cables in the ground. Well, putting those cables in the ground has a fairly big cost per, let's say, per mile to lay those cables underground. So when we're laying those cables, right now, with these new high-speed cables, I might say, ooh, let's connect these two really close data centers together, the red and the blue one right in the middle. And then, oh, well, let's connect it to like that yellow one nearby. At least I think it's yellow. You have to bear with me. I'm colorblind. And then we'll connect that to the blue one there. And then maybe we'll connect it down to the red one down here. What we wouldn't do, we would not make this connection there, because that connection would be a waste. You can still get from any one of those 5 to any of the others. You just might have to take 3 or 4 links instead of 1. But with our new super high-speed cable, hey, those 3 or 4 links are faster than the old 1 wire from the leftmost blue, purple one to the bottom red one. So we aren't going to make any cycles in our graph because it's so expensive to lay these cables. A cycle is a luxury we don't need. So we're just going to connect from one to another. And we want to do this in the way that has the lowest cost. And whether that's number of miles or total dollars spent, whatever it is, we're trying to minimize something that is a limited resource. We still want to connect everybody with this new high-speed fiber backbone, but we don't want to waste money on it either, and cycles would be a waste. So, the minimum spanning tree problem. So if we start out with a graph, edge-weighted, undirected, we're assuming it is an undirected graph here that's important on this problem. What we want to do is we want to find a subgraph of that graph that has all the same vertices, but it has a subset, E prime, that's a subset of the original edges, such that all vertices are pairwise connected. What pairwise connected means is you can get there from here. Maybe not in one link, maybe not in two links, maybe 3 or 4 or 7, but you can get a connection from here to there. So every vertex is connected to every other vertex directly or indirectly. And the other thing is we want the sum of all those edge weights to be the smallest possible. Because we're trying to reach that smallest possible, if we see a cycle in T prime, or T actually, it says remove the edge with the highest weight. So one way, this isn't the only way, and this isn't the way we're going to do it eventually, but one way we could do this is we could say, hey, I've got a graph, it's got cycles, and now I'm going to go into that graph and I'm going to remove any edge that has a large weight and produces a cycle. So the highest one that produces a cycle, we'll remove it, and we'll keep doing that until there's no more cycles. Now, like I said, this isn't the way we're eventually going to do it, but it's a way that works. So when we're done, T is going to be a tree. Well, that's in the name of this problem, tree. So it's going to be a tree because it has no cycles, and it's going to have the minimum possible weight. And the spanning, what spanning means is this. All vertices are connected. If it wasn't spanning, we would end up with a disconnected graph. So we want a tree, we want it to connect every pair of vertices directly or indirectly, and we want the minimum edge weight total. So for example, here's like I said, we'll run through an example of how we could do it by removing edges. So here I've got a graph, I've got my total edge weights, and every edge that could exist in this graph does. It's completely connected right now. So to turn this into a minimum spanning tree, let's start removing things that produce cycles. Let's remove the largest weight that produces a cycle. So this largest weight anywhere is 120. Let's remove that 120 and update it. Now we have a total weight of 300. We've reduced the weight. Everybody's still connected, but we still have cycles. So next highest edge weight is 100. Does 100 produce a cycle? Yes, it does. So let's get rid of that edge of weight 100. We're down to a weight of 200. It's still spanning, but there's edges that produce cycles. So let's look at the most expensive edge. 80 is the most expensive, but it doesn't produce a cycle, so it gets to stay. 60, next highest weight. It does produce a cycle, so 60 can go. And we've reduced our edge weight down to 140. Now there's no more cycles remaining, so we must have reached a point where we've got a tree. Okay, I'm pausing for a second. I see one person can't hear. Is everybody else doing okay? Is there anyone who can hear? My recording levels say it's good. It says excellent connection. I've got my volume turned off because I don't want to accidentally get a feedback loop here. Okay, so I'm sorry that it's not working for you, Mohammed, but if it's working for most people, we want to keep going. It could be just on your end, and you may have to go back and rewatch it later on. Hopefully, if you just reconnect or refresh your browser, you might get a better connection. Okay, well, thanks for the update, everyone. Okay, so let's go back to where we were. So we've got a tree now. It is still spanning, and since we've eliminated all the largest cost edges that we can, it should be the lowest weight possible. It should be a minimum spanning tree. Now, what I'd like you to do is take a few minutes and look at these questions and think about how you could prove. Okay, that's all right, Mohammed. I'm glad it's working again. All right, so what I want you to do is think about proving that the unique shortest edge must be included in every MST. And what we mean by unique here is there's an edge with a weight shorter than anyone else. So if there was an edge of weight 5 and no other edges of weight 5, that would be the unique shortest edge. And if there was an edge of weight 5 and an edge of weight 6 and everything else had a higher weight, that 6 would be the second shortest edge. And what about a third? What if we had a 5, a 6, and a 7 and everything else was higher than 7? Would that be true? So let's talk about for a second how you could prove this. So one way to prove this would be, I'll give you a second to think about it, proof by contradiction. So proof by contradiction would work on here. So go ahead and take a few minutes. I'm going to stop talking and work out how we could do this for 1, for 2, and see if we can extend it upward to 3. Okay, so you've had a minute to think about that. So let's say we want to prove this. So let's say we've got a minimum spanning tree, or a graph. Let's take a graph and let's make a simple one. Let's make it look like a right triangle here. So I have edges of weight 3 and 4 and 5. Okay, so if we do a proof by contradiction, let's assume the opposite. Let's assume that this unique shortest edge does not have to be in the minimum spanning tree. So we remove the edge of weight 3, and now we have a tree. It is spanning. We haven't lost any vertices. There's nothing we can't reach. But could we get a better weight out of this? Well, since I don't have any cycles, I would like to add an edge back into this tree. I'm going to add this edge of weight 3 back in. Well, now I have a cycle. When I've got a cycle, I've got to get rid of the cycle, so let's remove the edge of highest weight. Now I have a spanning tree again, and there's no way to reduce the weight. All right, let's say they're all in, and we say, okay, well, what about the second one? Let's get rid of the second one. Okay, so I get rid of the second shortest edge, and now I have a spanning tree. I would like the weight to be smaller, so I'm going to put the 4 back in. Well, when I put the 4 back in, I've got a cycle. If I want to have a spanning tree, I've got to get rid of the cycle. When I get rid of the cycle, I get rid of the edge with the highest weight, and I'm back to a minimum spanning tree. Okay, so first the shortest edge has to be in. Second shortest edge has to be in. What about the third shortest edge? Okay, third shortest edge, let's put the 5 in. Okay, well, now we've got a cycle. So if I've got a cycle, I can take out the edge of the longest weight. Oh, that is the 5. So the third shortest edge might be in there if it didn't produce a cycle. So for example, let's draw a slightly different graph. Let's say I've got vertices this and like that. Let's see. So we'll label these, and I think I messed this one up. Let's see. Let's put another edge in there. Okay, so now the third shortest edge definitely produces a cycle. Okay, that's not a good one. Let me clear that out and draw a new one. Okay, so here we go. So let's say these edge weights are 1, 1, 2, 3, 3. Granted, it doesn't fit in a plane like this, but let's pretend. So, first shortest edge is in there, second shortest edge is in there, third shortest edge can't be in there because it would produce a cycle, and now we can pick one of the 3s but not the other one. So the third shortest edge won't be in there if it produces a cycle, it will be in there if it doesn't produce a cycle. Okay, and that's just a different page for doing all of that. Okay, here's another one to take a few minutes to try to build up a couple graphs. So, build a graph, show me a graph that has more than one MST. And what I mean by more than one MST is they have the same total weight, but different edges. Okay, let's get all of these listed, and I'll give you some time to think about them. Okay, so after you do a graph with more than one MST, show me a graph and its MST which avoids some shortest edge. And for it to avoid some shortest edge, we'd have to have more than one edge with lowest weight. Okay, show a graph where every longest edge must be in every MST. This one's a little bit harder. Oops, sorry, I moved on to the next page. I thought there was a fourth one. Okay, so make a graph for each of those 3, and it is possible for some of these to have the same graph. The first 2 especially, you can demonstrate with the same graph. So work on those for a few minutes, and then we'll come back and talk about them. And the first 2 of these are fairly easy. It's the third one that's a little bit harder sometimes. Okay, so let's look at some of these. So the first one, show a graph with more than one MST. We could do it with a triangle. We could do it with a square, would be easy also. If I had a square where every side is of weight 1, then to produce, if those are the only edges that exist, like I didn't have edges across the middle, if those are the only edges that exist, I've got to get rid of one of those edges because I've got a cycle. If I get rid of any one of those edges, if I say get rid of that one, or I could get rid of that one. I would have two different MSTs because they have different edge choices. And let's label our vertices, A, B, C, D. So I might have a graph where I've got like the edges AB, AD, and CD are the three edges that I picked. That would be different from the MST where I choose AD, CD, and BC. So they both have a total weight of 3, but they are different graphs. We'll get to you on number 3, Alex. Yep. So that's a graph that shows number 1. We've got more than one MST because we've got actually 4 MSTs. For number 2, we can use the same graph because we've avoided some shortest edge. We avoided edge AB or BC, etc. And for number 3, so what someone typed in there, yeah, if we just had a graph with one edge and 2 vertices, then it satisfies it. Usually people don't go that small. But we can actually make number 3 more general than that. That works. Great example. In number 3, if I start out anything that's a tree to begin with, if there are no cycles, there's no edges that can be removed. Therefore, every longest edge is in there. So 2 vertices and 1 edge is a tree because it has no cycles. 3 vertices and 2 edges, still a tree, etc. So really, if we have V vertices and V minus 1 edges, then that would satisfy number 3. So what we're going to talk about today is 2 different algorithms for finding an MST, and they operate under the same conditions. We've got a connected graph, it's edge-weighted, and it's undirected. And what it's going to do, or what each of them is going to do, is it's going to proceed in a greedy manner. And we've got a bit of a chicken and egg problem here in that greedy and algorithm families is a lecture that's coming up, but we need to cover this, and it's a good time for this. So let's talk about what greedy means for a minute. So in terms of greedy algorithms, what that means is that they always make the best choice that they can make right now. So based on the information that is available right now, it makes the best decision it can, and it never goes back and changes its mind later on. So some problems are solvable with greedy algorithms all the time. Some algorithms are solvable with greedy algorithms only if the data fits how the greedy algorithm works, and others it just doesn't apply. So these 2 algorithms use the greedy approach, make the best choice you can right now and never change your mind later, and they are also optimal. They find a minimum spanning tree. We can't say the because there might be more than one. We just showed that. So both of these algorithms use a greedy approach, and when I say make the best choice you can right now, you always make a valid choice. You never make an invalid choice just because it has a low cost. You make the lowest cost valid choice at any given time. So as these proceed, Prim is going to start at a vertex. Prim's going to start at a vertex, and it's going to add edges, and it's going to grow a tree from that one vertex until the tree is a spanning tree. Kruskal is possible for it to grow a forest, and what that means is you might have, so in Kruskal you might say, ooh, let's connect these 2, and then let's connect those 2, because those are the shortest edges I could grab. And then later on, eventually, those 2 regions will be connected together to produce a minimum spanning tree. So prims will always grow from one vertex, and then every edge it adds will be added to a vertex that is already in the chosen set, whereas Kruskal will potentially grow a forest. Kruskal might grow a tree, but it usually often grows a forest. It doesn't care. Okay, so let's look at Prim's algorithm overall, and then we're going to look at an example soon. So we're going to go through a couple slides of rules and then we'll look at an example and make it a little bit clearer. So we're going to start out with a graph, and in that graph we're going to say, hey, let's start making our minimum spanning tree by picking a single vertex. Arbitrarily. It doesn't matter which one we pick, we'll still get a minimum spanning tree. So we choose that edge, and then what we're going to do is we're going to say, hey, let's pick an edge that connects the tree that we have so far to some vertex that isn't in the tree. Of all of those possible edges, of all the edges that connect our tree that we're growing to vertices that we haven't added, pick the lowest cost edge that connects our tree to a vertex not in our tree. And then we just go back to step 2. So we keep doing that until all the vertices are in the tree. And we know we're going to have to do this enough times. Basically, every vertex has to be in the tree. We've got to do it enough times to have v-1 edges. So, Prim's algorithm, we're going to start out with a graph, V and E, and this is one way to think about it, but it isn't necessarily the best way to implement it. So we're going to talk about implementation a little bit more later. So we're going to start out with a graph of vertices and edges, and we're going to separate them into the ones that are in the tree and the ones that are out, the ones that are not in the tree. The ones that are in a tree, that set it is initially empty, and outies is all of them to begin with. So then we're going to select our first vertex. We could think of it as the root of our tree, but since it's not really a directed graph, we're not going to have like arrows connecting them. But we think of it as our starting point. So the starting point is the root of our tree. So we select one, we move it from the outies to the innies, and then we keep going until the outset is empty. We choose the outset vertex with the smallest distance from anyone who's in, and we move that one over. And there's another big implementation issue. Should we use searching to find the best one, or should we use a priority queue? So we'll come back to that question. So really what we want to do is the simplest approach to implementing this is don't worry about insets and outsets. What we're going to do is we're going to make 3 vectors. Better yet, let's make a vector of structures. So in each structure, in the structure, we're going to record for each vertex, we're going to remember K. Do we know the best way to pick this vertex? Initially, that's false for everybody. Then our distance, what is the minimum edge weight to V? Initially, that's infinity for everything except for the root. And the P is who is the parent, or who's the predecessor of this vertex. And we're going to need those so we know what edges we chose when we're all done. So let's look at this, and then we're getting to an example really soon here. Okay, so we're going to set our starting point. We're going to pick our starting vertex, and we're going to set its distance to 0. And it says set its predecessor to null. Really, everybody's predecessor is going to be null to begin with. We're going to loop v times. So we're going to loop v times through this. Notice in step 2, we're going to mark one vertex as true. Because step 2 marks one vertex as true, this loop has to run v times. So step 1 is find this from the set of vertices for which kv is false, select the vertex v having the smallest distance dv. So basically step 1 says find us the smallest false one in the table. Step 2 says set it to true. Step 3 is basically updating the neighbors. Of the one that just went in, does the one that just went in give anybody else a shorter distance to an innie than they used to have? So we've got a big loop around the outside here, and that's always going to be true. One way to implement this is to have a loop for step 1 and a loop for step 3. Now notice it says up front, before the loop starts, set our starting vertex distance to 0. Now I'm going to give you a warning because this is something that gets me a little bit perturbed during office hours because I keep saying don't do it and people keep doing it. And it's possible to ignore me and get it right, but it's lots of people who ignore this get it wrong when we get to project 4. So what lots of people want to do is they want to say, hey, that vertex distance 0, I know it's true. I'm going to set it to true outside the loop. Don't do it. Resist the urge to set anyone to true outside the loop. So we wanted, when we get to project 4, when you get the project spec and start working on it, one part of project 4 is going to be MST, and it's not going to be too hard. It's going to be a good amount of points for not an insane amount of work. And if you listen to me now and implement it this way later, you'll have less grief in your implementation. So we're going to loop, we're going to have that outer loop, looping V times. Step 1, we're going to loop and find the smallest false one. Step 2, we mark it as true. Step 3, we loop over all the vertices and update the false neighbors. And if you reorder this, if you say, ooh, I'm going to mark KV as true outside the loop, then I'm going to start the loop with step 3 and then do step 1, and then I'll do step 2, and I'll reorder this. If you reorder this, it produces a little bit simpler implementation that is easy to get wrong. So keep it in this order. So let's run through an example. And the way I would like you to implement it and the way that it's easier to get it right is exactly the way we're going to do this example. So we started out, and really, like I said, everybody doesn't know who their predecessor is. Nobody's got a predecessor. Everybody is infinite distance except for an arbitrary starting point. Why did I pick A? Because it was the first one alphabetically. When you implement this for project 4, the vertex names are going to be their indices. So vertex 0 is at index 0, vertex 1 is at index 1, makes it super easy to start at vertex 0 and say, oh, vertex 0, you've got a distance of 0. Because you know, if I gave you any vertices, there's got to be a vertex 0. So we pick one arbitrarily. First one is an easy arbitrary pick. So we start that one at 0, and then what we're going to do is, now we've got to run the loop. So until everybody is true, we run step 1. Step 1 says, find me the smallest false one. Okay, let's figure out what's the smallest false one. So my current vertex, let's say my current vertex is, let's assume A is the smallest one. We run through and we never find one better, so A is my current vertex. It's the smallest false one. Step 2, mark it as true. Okay, we mark that vertex as true. And now step 3 is run through anyone who's false and happens to be a neighbor of A, figure out if you've found a better way to reach them. Okay, so let's run through them. So let's say we do it from top to bottom, the way we would write a loop. So we go from top to bottom. A is already true, we can't touch it. B is false. B has a distance of infinity, but I can get from A to B at a distance of 13, and that's better than infinity. So I update this distance to be 13. And I also here, we have to change who is the predecessor. We now know who is the predecessor of B. Well, it's whoever the current vertex is B's predecessor. So when we update the distance, we update the predecessor. If we don't update the distance, we leave the predecessor alone. So we update the distance to be 13 and the predecessor to be A. Then we look at C. Okay, C is false, so we can check it. Distance of infinity, but I can get there from A to C at a distance of 8. 8's better than infinity if I use A to get there. Oh, that's a sad-looking 8. It almost looks like a 0. Okay. D. D is false. D right now is a distance of infinity. A to D is 1. That's better than infinity. So we update D's predecessor to A. Distance. Sorry. Distance to 1, predecessor to A. All right. We go to vertex E. E right now is false. it has a distance of infinity, and there is no edge from A to E. Effectively, think about this. You're MST and I am your distance calculator function. You call me with A and E, what do I return to you? Numeric limits of double infinity. You get an infinity from me and you look at it and you go, wait, is infinity better than what's in the table right now? No. So I don't update E. What about F? You ask me, what's the distance from A to F? I say infinity. You, MST, say infinity, that's not better than what's in the table. We don't update F. All right, we've gone through one vertex. So let's go to the next slide. And now we have updated all the neighbors, and we're at a new point here. So we've got to go back to step one. Step one, find me the smallest false one. So right now, the current vertex, I don't have a current vertex. I look at A, I see A is true. I can't use that one. I'm looking for the smallest false one. I get to B, I say, oh, B has a distance of 13. Okay, that's better than, let's say I had really, actually, let me change that slightly. So I've got my current vertex and I've got my current distance. My current distance, let me just rewind this one more step. Initially, I don't have a current vertex, but I do have a current distance. The best distance I know is infinity because I don't know anything. Now let's loop through. I look at A is true, can't consider it. I look at B is false, so I can consider it. B has a distance of 13, that's better than infinity. So B at 13 is the best so far. Check C. C is false. It has a distance of 8. 8 is better than 13. So right now, I think my current best vertex is C. All right, let's check D. D is false, so we can consider it. D is a distance of 1. That's better than 8. So my current vertex is D so far. We're still doing step 1, though. We get to vertex E. E is false, but infinity is not better than 1. Go to F. F is false, but infinity is not better than 1. I've found my current vertex. So step 1 is done. Found my smallest false vertex. Step 2, mark it as true. That's easy. Now what I've got to do is I've got to update all of the neighbors of D. So let's go through the table from top to bottom, updating neighbors. I'm going to change colors here. Okay, so we go through top to bottom, updating neighbors. I say, okay, A is true. We can't update anybody that's true. B has a distance of 13. What's the distance from the current vertex D to B? Oh, that's infinity. Infinity is not an improvement. We leave it alone. All right, what about C? C currently has a distance of 8. To get there from D would be a cost of 5. That's better than 8. So let's update this to be 5. And we update the predecessor vertex to be D. All right, next vertex. D is already true. We leave it alone. Next vertex, E. E is false, so we can consider it. E has a distance of infinity, but D to E is 4. 4 is way better than infinity if we use predecessor D. Vertex F. F has a distance of, F is false. F has a distance of infinity. We can get from D to F in 5, way better than infinity, if we use D as our predecessor. So that's the end of step 3. We've updated all of the neighbors of D that we're able to update. We skip the true neighbors and we skip the ones we can't improve. All right, next slide. After we've run through the outer loop twice. Okay, I'm going to fast forward this time. So now we're going to worry about what's our current vertex and our current distance. Okay, so the smallest false one. Looks like the smallest false one is E at a distance of 4. Let me change one thing to give you a what if. What if this was a 6 and that was a 6? then I would say, ooh, my smallest false one could be C or it could be F. It doesn't matter which one you pick, because you will either pick both of them or you would pick one of them but not the other, and you'll end up with different equivalent MSTs. So if I was coding this, I would tend to write the code to say, hey, 5 is the best so far, 5 is not better than 5, so I would choose C to be my closest, my current vertex. But it doesn't matter. As long as you pick one of them, it's going to be right eventually. Either you'll end up choosing both edges of length 5, or you'll choose one and not the other, and you would, if you chose a different 5, you'd get a different MST. So that's sort of a what if, just if things were equal. Okay, so let's go back to where we were with the current vertex and the current distance. Okay, so current vertex. Smallest false one is E at a distance of 4. That's step 1, we found it. Step 2, mark E as true. And then step 3 is update E's neighbors. Well, when we go to update the neighbors, we go to B. Oh, we can't get there. What about C? C is false. I can get to C now at a distance of 3, which is an improvement. I can get to C at a distance of 3 if I use E. D is already true. We can't touch it. F is false. It's a distance of 5, but I can get from E to F at a distance of 2. That's better than what we've got so far, so we update that one to be 2, and the predecessor is going to be E. Okay, so that's step 3 is done. We've updated all the neighbors. Let's go to the next slide. All right, we've got to go find the current vertex, and we'll remember the current distance. So we find the smallest false one. Smallest false one looks like F at a distance of 2. That's step 1. We look through all of them. So step 1 is find the smallest false one. Step 2, mark it as true. Step 3, update the neighbors of F. Well, the neighbors of F, if we loop through, remember we're looping, we loop through, we go A is true, B distance to F is infinity, C distance to F is infinity, D is true, E is true, F is true. We're done with step 3. There was no one to update. So next slide. So now we've got to find the current vertex, current distance. Okay, so we find the smallest false one. It looks like C at a distance of 3 is our smallest false one. Step 1 is done. Step 2, mark C as true. Step 3, let's update the neighbors of vertex C. So A is already true, B is false, but the distance from C to B is 15. 15 is not better than 13, so we leave it alone. Then we look through the other neighbors. D, E, F are all true. We're done updating neighbors. So next slide. So step 1, find the smallest false one is B at a distance of 13. So that was step 1, find that one. Step 2, mark it as true. Step 3, update the neighbors. Well, every vertex is true. There's no one that can even be considered for updating. So we're done. Now, the table tells us everything we need to know about our MST. In the table, if we sum up the total distance column, we got 13, 16, 17, 21, 23. 23 is our distance. And if we look through the table at every one that does have a predecessor, see row A doesn't have a predecessor. Row A, and we knew that. We started out there. So I can really, since we said, hey, let's just choose index 0 to be the root, I don't even have to consider it. I don't even have to look for someone that doesn't have a predecessor. I just say, hey, if I'm going to list out the edges, let's start at index 1. Let's start at vertex B. And my edges I could list out as BA, CE, DA, ED, and FE. Now, when you get to project 4, the MST part, when we have you list out the vertices, there'll be a couple of small changes. One change is that the vertex names will be numbers. So instead of like B and A, it would be 1 and 0. And the other thing is that when you output them, we want you to list them in smallest vertex first. So and you're just going to put a space between them. So instead of that, if this was like real project 4 output, what it would display first would be the total 23.00, and then it would display the edges would be like 0, 1. Let's see, CE would be 2, 4, AD would be 0, 3, 3, 4, and 4, 5. So that, and pretend there's a space in between those. I got a little bit cramped there. So we just put a space between each of them. So we'd list out the distance first, followed by the list of edges that are in that MST. All right, I haven't seen any questions lately, so I guess we're doing okay with this. So I'm going to pause for a few seconds, wait for any questions to come up, let you think about it, and actually, let's go to, here's the next slide. The next slide is, I'd like you to do prims on this starting at node A, meaning A is going to get the distance of 0. So you can start making a table. If you've got questions, ask them now while people are starting to work on this, and I'll put up the next slide is just an empty table. So in the empty table, I could start out putting in, the distance A is 0, infinity, infinity, infinity. That's some terrible infinities, and we don't know any predecessors. Okay, so if you've got a question, type it in, and if not, take a few minutes to work on this. What I meant, Alec, was, let's go back a slide or two, for a given edge, not in order of weight, in order of node name. So I've got the edge 1, 0. Instead of outputting 1, 0, I would output 0, 1. So I don't have to sort the edges in terms of their weight. It's just that for a given edge, in order from top to bottom, I'm going to output them. Instead of saying 1, 0, I would say 0, 1. I will list the smaller node first, followed by the bigger node. Okay, so that's questions answered here. You can work on this for a few minutes, and we'll come back after you've had a chance to work on this, and we'll work through this one. I'll tell you a few more things about how the project 4 grading goes. Okay, so let's go through a solution to this one. So when we start out, I'm going to make just one entry for the current vertex. So the current vertex, we go through the loop v times, find the smallest false one as A, then I mark K as true, and I didn't write false for all of those, but if there was Boolean variables there, they would have all started out as false. So I mark A as true, and then I have to go through, so that was step 2. Step 3 is update the neighbors of A. Neighbors of A, let's see, B is at a distance of 1, that's better than infinity. If I use the predecessor, and I'm gonna do a little bit of erasing here to make sure I've got enough room to finish this, because I've only got one slide for this. Okay, so I've got infinity, nobody, infinity, nobody. Okay, so B has a new distance of 1 if I use vertex A. Vertex C has a distance of 3, which is better than infinity if I use vertex A. And I can't reach D or E from A, so I can't update them. Okay, so we've gone through the outer loop once. Let's go through the outer loop again. So I go through step 1, find me the smallest false one, looks like B. Step 2, mark B as true. And then step 3 is update the neighbors. So really, step 3 is going to be a loop. We're going to go through everybody. I start at A. I say, okay, A is already true, can't change it. B is true, can't change it. C is false. I can get to C at a distance of 4, but that's not better than the 3 that's already in the table, so I leave that alone. D, I can reach at a distance of 6, which is better than infinity. If I use vertex B, I can get to vertex E at a distance of 7, that's better than infinity, if I use vertex B. Okay, so that step 3 is done. Go back through the outer loop. Step 1, find the smallest false one. Okay, smallest false one is C. Step 2, mark C as true. Step 3, update neighbors. So we go through everybody. A is already true, B is already true, C is already true. D. D is a distance of 6, but I can get from the current vertex C to D at a distance of 5. Let me change colors here. So 5 would be better than 6 if I use C. And then I can get to E. Nope, I can't get to E from C. They're not connected, so don't even look at the distance, because it's, well, I'd say the distance is infinity, so it's not better than 7. Okay, we go back, we're done with step 3, go back through the outer loop. Vertex, let me change colors again now. Vertex D, D is my smallest false one. I mark D as true. So that's step 1 and step 2. Step 3, update the neighbors. True, 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 true. Aha, E is the only false one. I can get from the current vertex to E at a distance of 2. 2 is better than 7. So I update that to be 2, and I update the predecessor to be D. So step 3 is done. I've updated all the neighbors. So I go back through the outer loop. Step 1, find me the smallest false one is E. Step 2, mark it as true. Step 3, update the neighbors. Well, everybody's already true, so we're done. With step 3, the outer loop is done because we've gone through it V times. And then we look at the column of the distances. So we've got 1 plus 3 plus 5 plus 2. So that's 9, 10, 11. So my output for this would be like 11.00. And then I'd output the edges. Well, we don't start at row 0. We start at row 1. So that would be BA. Really, BA would be 0, 1. CA would be, well, BA would be 1, 0, but we order the vertices in smaller to larger order. So we display 0, 1. The next one, CA, would be 2, 0. We would display 0, 2. DC would be 2, 3, or 3, 2, so we display 2, 3. And then ED would be 4, 3, we would display 3, 4. Now, one thing about the all of the parts actually of Project 4. How the autograder works is after you produce output, we run your output through a program we call the judge. And the judge decides if you were right or wrong and what feedback to give you if you were wrong. The judge up until now has been basically the same. Your output must match our output. For Project 4, every part of the project has a different judge, and every one of these judges says, does your output make sense? Is your output an MST? So I'm going to move on to the next slide before I do an example because I'm running out of room here. So there's the MST for that one. We've already listed the total weight and we've listed which edges are in the MST, are the ones that are in the table. Now, what I was talking about is your output must make sense. Suppose I gave you this input file. I say, hey, there's 4 vertices, and this is like a preview, but let's forget the input. Suppose I told you this. Here's A, B, C, and D. And let's say every edge was in there, and the edges are length 1, 1, 1, 1, 1.4-ish, 1.4-ish, square root of 2. So if you went to output an MST for this, well, you better have 3.00 for the total weight of the MST. But you could list the edges as like 0, 1, 1, 2, 2, 3, or you could say 3.00, 1, 2, 0, 1, 0, 3 would be another valid output. And the autograder for Project 4 will grade both of these correctly. It'll say, hey, you've got the right total weight, you've got the right number of edges, the edges that you told me do make an MST, and the edges that you told me do add up to the 3.0 that you said it does. And so you've got a valid output. However, if you said my total weight is 3 and I have an edge from 0 to 2, which would be from A to C, we would say, hey, wait a minute, you've got the right total, but these edge weights don't add up to 3, they add up to 3.4, etc. So as long as the output makes sense and makes a valid MST, it doesn't matter if it's the same as ours. It could be in a different order, it could be different edges selected, it could be both. As long as it makes an MST, it'll be judged to be correct. So that makes it a little bit easier to have a little bit different implementation from us and still have valid output. When we give you output, like in our sample output, we will actually give you output in the order that they're discovered. So like back at this example here, we would be outputting them like basically the order that the edges got selected, where D was the first vertex selected and AD was the first edge that was in the MST. We would list AD first so that when you debug, you can sort of see that from our output. Okay, so let's talk about the complexity. So we're going to do the complexity first the way we talked about implementing it, which is basically step 1 is a loop, step 2 is a loop. So on this one, the outer loop is going to run V times. Another implementation thing. I've seen people do things like, while my function says I'm not done, and the function goes through a loop to check if every one of the vertices is true or not. That's a waste of time because we know if step 2 sets one of them to true and we've got V vertices to mark true, the outer loop really, this can just be a for loop. For I equals 0, I is less than V. So really, we don't want really a while loop or a do while or anything. Make it a for loop. Run it V times. Okay, so step 1. Step 1 is basically looking at every vertex. If it's false, and its distance is better than the best so far, update the best so far. So that's O of V. Step 1 is a loop that runs over V times. Step 2 is O of 1. Look it up in the table, mark it as true. Step 3, really, if we think about it, step 3's got to loop over everything. Step 3 is going to say, okay, vertex I, or let's say vertex J. Loop 3 is going to loop over vertices from j equals 0 to the end. It's going to say, hey, vertex J, are you already false? Is the distance that I can reach you now better than what's in the table? If those are both true, we will update what's in the table. Otherwise, we don't. So the most that we can possibly look at is V. We look at every vertex. Some of them are true, some of them are false. Some of them are false and not an improvement. Some of them are false and they are an improvement. But we've got to look at all of them. Basically, loop 3, the cost of loop 3 is V. So I've got a loop. I've got a loop around this outer part. I've got a loop running V times. Step 1 is a cost of V. Step 2 is a cost of 1. Step 3 is a cost of V. Gives us V times 2V plus 1 is equal to 3V plus V. Gives us O of V squared. Oops, sorry, 3V squared plus V, sorry. 3V squared plus V. Or no, 2V squared. 2V squared plus V. I can think just fine. Doing math is hard. Okay, so that's our cost if we do it with loops, is V squared. Let's say we did it with a priority queue instead. So when I say heap here, I mean a binary heap or a priority queue. So what we're going to do is first we got to do some initialization. I've got to figure out the number of vertices in the table. Well, that's easy. However big the vector of vertices is, that's how big it is. That's n. O of 1. Create the table. Creating the table takes O of V time because we've got to initialize all of the k's to false, all of the distances to infinity, all the predecessors to, I don't know who my predecessor is. We said it would be null, but really, if we were implementing this, what would I do for a predecessor? It would be like an unsigned integer. So I just need to decide on an unsigned integer that means I've got no predecessor. Really, it doesn't matter. If it's 0, I only look at the predecessor. I only look at who your predecessor is when I know that it might have one. When might it have one? When the distance is something other than infinity or something other than vertex 0. Okay, so it takes us O of V time to create that table. Then to create an empty PQ is O of 1. I'm going to mark vertex S0, my starting vertex. So I mark my starting vertex's distance as 0. That's O of 1. And I add something to the priority queue. Basically, I put into the priority queue S0, vertex 0, is a distance of 0. Now, inserting that into the PQ right now is O of 1 because it's empty. So adding something to an empty PQ is a cost of 1. Okay, next step. Here's the big loop. So the big loop says while that PQ is not empty. So now I'm gonna do this like we did, kind of like project 1. I take the next thing out of the priority queue, I do something with it, I add things nearby, and I keep doing that while the priority queue is not empty. Now, how many times could this while loop run? This while loop can't run more than E times, because every time I add something to the priority queue, I'm basically adding an edge. I'm saying you can get to this vertex in this distance, and that can never happen more than there are edges in the graph. So this outer while loop is never going to run more than E times, because I'm never going to have more than E edges. So now it says, get me a new possible best so far. Get me a best so far, which is basically doing a top and a pop. So top is easy. Top is O of 1. But the pop part is log of E. It's log of E because that's how big the priority queue can possibly be. It'll never have more edges in the priority queue than exist in the graph. Therefore, the upper limit on how long it could take to pop something out is log E for a binary heap, for a PQ. Okay, then we check, it says here, if this vertex is not already known. If this vertex is not already known, we've got to do a bunch of stuff. Notice there's no else clause, and basically in pseudocode we don't have curly braces, but really that's the end. There's the end of the if, and here's the end of the while loop. So if it is known, we skip it. And we go and we get someone else out of the priority queue. Now, why would that happen? If we look back just a little ways here to this example, at one point, remember, we added D at a distance, change colors here, we added D at a distance of 6. So we put D at a distance of 6 into the priority queue, and we put E at a distance of 7. Those went into the priority queue. But then before we used them, D at a distance of 5 went into the priority queue, and E at a distance of 2 went into the priority queue. These came out first. When this comes out later on, when D at a distance of 6 comes out, we say, hey, D is already true. This info is outdated. It looked good as a choice at the time, but we improved upon it, and we took the distance 5 out first. When distance 5 came out, D got marked as true. If D at a distance of 6 comes out of the priority queue, we ignore it because D is already true. So that's why the if statement is there, is to prevent us from looking at vertices that we already know the best way to get there. Okay, so if this thing is not true, we mark it as true. This is step 2. Mark it as true. This was, right here, this was step 1. Oops, step 1. Step 1 was get the smallest false one. Well, really, it's not quite step 1. It's get the smallest one. Get the smallest one, and if it's not false, we throw it away and we go get another smallest one. So this is kind of like step 1, is get the smallest one, and if it's not false, we throw it away and we get another one. This down here is step 3. Let's go update the neighbors. Okay, so step 2 has a cost of O of 1. We just mark it as true in the table. And then we've got to figure out what is the new distance that we're thinking about. The distance from V0 to VI. Oh wait, I forgot the for loop. So the for loop, I'm going to run this for loop. I've got to go through everybody adjacent to this vertex. So V0 is my new closest false one. I've got to run through everybody that's adjacent to V0. There are at most, whoops, I leaned on my button and I changed to the wrong slide. Sorry about that. Okay, so when we look at going through the adjacency list of vertex 0, everybody in the adjacency list of vertex 0, it's a cost of 1 plus E over V. 1 to get to head of the linked list, E divided by V to loop through the average number per linked list. Remember when we did that just last time? You're going to see this over and over again whenever we deal with adjacency lists. That's the length of the average linked list as E divided by V. So that's how many vertices I have to run through that are adjacent to V0. For each of those, I figure out what is your distance to vertex 0. That's O of 1, just calculating distance. Then I do an if. If that distance is better than what's in the table, that's O of 1, change the distance in the table is O of 1, change the predecessor in the table is O of 1, and then we add something to the PQ. We add this distance with vertex I to the PQ, that's O of log E. If it takes log E time to pop something, because the priority queue is at most size of E, then it takes log of E to push something to that same priority queue, which never is bigger than the number of edges in the graph. So there's the bulk of the work. When we're all done, we got to go through the total here. So I've got a loop that's running E times. Inside of it, there's a so I've got E is outside times log E plus a bunch of constants. There's a bunch of O of 1s in there. But then I've got a for loop that's going to run E divided by V times and this is multiplied by what's inside of it, which is a bunch of constants plus log E. So now this looks pretty complicated, but let's look at this E divided by V term. If we're talking about a sparse graph, because hey, remember we said go through the adjacency list. If we're in a sparse graph, remember E is proportional to V. So E divided by V is approximately a constant. If that's a constant, then this is E times log E plus a bunch of constants plus log E gives us O of E log E. So that's if it is a sparse graph. So when we do the simple nested loop implementation, we get O of V squared. If we do the priority queues, we get O of E log E. But that E log E, think about what happens. If it's a sparse graph, we've got E log E is approximately the same. So if it's a sparse graph, in a sparse graph, E is approximately equal to V, and so E log E is basically equivalent to V log V. Now, what if it was a dense graph? In dense graph, E is proportional to V squared, which means that E log E becomes V squared log V squared. Now, it will actually be a little, it could be a little bit better than that. It could be like V squared. We can move the square here out front, so that would be big O of V squared log V. Because remember, we can move this 2 outside of the log, and then we get rid of the constant. So this one, it's not that the O of V squared is worse than E log E. It's that if we have a sparse graph and we do the priority queues, we get a better complexity than a dense graph. Okay, I'm going to pause here for a minute, wait for any questions on Prim before we move over to Kruskals. Any questions on the complexity here? Okay, well, I don't see any questions coming in, although I don't know exactly what my delay is, and I can't check my delay because if I start turning on the audio so I can hear myself, we'll get a feedback loop, and that would be terrible. Okay, so what we're going to look at next is Kruskal's algorithm. So Kruskal's algorithm is also greedy. It's going to work on the same sort of graph, edge-weighted, connected, undirected graph. And what we're going to do in Kruskal's algorithm is we're going to start out, we're going to sort the edge weights. We're going to sort the edges by their weights, and that's going to take us E log E time, which is the same as E log V, whether E is proportional to V or V squared, but E log E time. Now, this right here, I can tell if it's a dense graph, this is not a good idea. Because if this is a dense graph, I'm at V squared log V just for the sorting step, and I haven't done anything else yet. So Kruskal's is really only good for a sparse graph because of that sorting step. Okay, so then once I've got the edges sorted in order of increasing rate, I'm going to try to add them to the forest. I'm going to try to add them to the forest in a way that doesn't produce cycles. So from the sorted order, I get a next potential edge. We already proved the shortest edge has to be in the MST, second shortest edge has to be in the MST, the third shortest edge might or might not, depending on whether it makes a cycle, and from there on. So we could have a disjoint set of trees to begin with, and we might produce a forest, but eventually when we're done, they'll grow together and produce one tree. So let's look at an example of this one before we look at more details. All right, so here's Kruskal's algorithm. Now we could go through, list all the edges and their weights, sort them using our favorite sort in our head, but if the graph isn't too big, we can kind of do this visually. All right, so let's do this together. Let's find the shortest edge. Shortest edge looks like an edge of weight 1 from A to D. Aha, that one's in because it didn't produce a cycle. So there we go. That one's in the graph, and I recolored the vertices there to say, hey, I've chosen this edge. That means these two vertices are connected together, and then we find the next smallest the next smallest one, period. So we find the next smallest one is 2. Does that produce a cycle? No, so we can put that edge in the graph. There we go. Colored this differently because it's part of a different connected section. This is the demonstration of why it might be a forest. So we might add some edges to one, add some edges to the other. Eventually they'll become connected. All right, so next smallest edge is an edge weight 3. Does the edge of weight 3 produce a cycle? No. Okay, so the edge of weight 3 could be in our graph, and there it is. Next shortest edge looks like 4. Does 4 produce a cycle? No. Since it doesn't produce a cycle, 4 is in the graph, and it connects 2 previously disconnected trees into one tree. So we knew it would happen eventually. So we recolored those to show that they are now part of the same connected area. All right, edge of length 5. I've got 2 choices. Which one would I encounter first? I don't know. It depends on how I sorted them. If I sorted them without a tiebreaker, it could be either one. If I was going to put a tiebreaker, I'd say smallest vertex first in the sorted order. So that would be this one. Does it matter? No. Partly because, oh look, that one's not in because it would produce a cycle. And this one, the other 5, not in because it would produce a cycle. So the order here doesn't matter. Either we're not going to pick them at all because they both produce a cycle, we'd pick them both because neither produces a cycle, or we'd pick one and not the other, and we'd end up with different MSTs of the same weight. So it doesn't matter. All right, next shortest edge that we haven't already picked or disallowed looks like edge of length 8. Edge of length 8. Oh, that produces a cycle. Can't have that one. All right, how about an edge of length 13? Edge of length 13 does not produce a cycle. You're in the graph. edge of next smallest edge is edge of length 15. You would produce a cycle, you're not in. Now a simple way to write this is just go through the sorted order. If it would produce a cycle, we don't put it in. You could also loop and keep track of how many you have added, because we've got to be able to loop through it until there are enough edges in our graph. I'll get to your question in just a minute, Daniel. So if we're going to loop through this one, once we choose v minus 1 edges, we could stop right there. As soon as we've chosen v minus 1 edges, we could know we're done, or we could just keep going through sorted order until we've gone through every possible edge. Doesn't matter much because it's going to be right at the end. Okay, so the efficient way to check for cycles. Yep. The efficient way to check for cycles, this is going to go back to something we covered earlier in the semester, which is union find. So we'll get back to that in a minute. We're going to do union find in a few minutes. So when we do Kruskals, the sorting, it takes E log V, which remember is the same as E log E, because E is either E is proportional to V in a sparse graph, E is proportional to V squared in a dense graph, but log of V squared is the same as 2 log V. So that's why we said this. We could also say this. Either one is correct. So the sorting takes E log E time. Then what we're going to do is we're going to loop over all of those E edges. Discarding an edge is trivial. I don't do anything. Adding an edge is easy. At the worst, I might keep like a vector of which edges I've chosen. So if I had a vector of which edges I've chosen, adding an edge to that vector of edges I've chosen is amortized O of 1. Really, it could be O of 1 because I know I'm going to pick V minus 1 edges. I could pre-size my vector of selected edges to be like reserve V minus 1, and then the push is guaranteed to be O of 1. It's not even amortized. So discarding an edge is trivial. We do nothing. Adding an edge is O of 1. I add it to a vector. And the most time I'm going to spend is looking for cycles, as someone said. So the good news is, as long as we spend less than log E time, remember, this loop is running E times I've got to do this work. As long as the time spent checking for a cycle is less than log E, then E times the total is going to be less than E log E. So the key here is I only connect two vertices when they aren't already connected some other way. So we need to do the union find here. Remember what we said about union find. The example we used in class was if we were laying like little railroad tracks between new colonies on Mars, and we said that cycles would be a luxury on Mars. It's so expensive to lay those tracks. Same as here on Earth, we're laying fiber optic cable underground, expensive to dig those holes and pull it through underground, etc. So we're not going to allow cycles, and we want the lowest cost way to do it. See, when we did the thing on Mars, we were just worrying about getting them connected, period. Here, we're worried about getting them connected and having the lowest total cost to do it. So the preventing cycles is going to be one part of that. So we're going to use the union find data structure. We're going to do everything that we did before. We're going to do the representative of a representative of a representative. We're going to compare representatives. If you have the same representatives, you are already in the same set and you can't be connected. If you have different representatives, we can update you, we can do the path compression, etc. And remember, we found that if we do all of these things properly, we get the overall complexity to be n alpha n, which is the same as here n would be E. So that would be O of E, alpha of E. But remember, alpha of E is almost always less than 5. For any practicable number of things we will ever consider, it's going to be less than 5. So this E alpha E is basically proportional to E times 5. So the part that does the checking for cycles back here, the checking every edge and preventing cycles, this whole loop right here is our E. Alpha of E is the time for that loop. Okay, so that's the time for the everything but the sorting. So the sorting is E log E. The rest of it is E times basically a constant. So that gives us E log E is our time. Okay, so what we've got here is another one to run, sample through, doing Kruskals. So I'm going to start you on, I'm going to show you the next slide that's hidden. It just has a little bit of prep work. So here's our prep work. I sorted them in order from lowest weight to highest weight for you. Makes it a little bit easier. I've got the vertices and their representatives. You can solve this without ever updating the representatives. Just visually make sure there's no cycle. Now, I won't say we won't ask you a union find question on the exam, but I will say if we ask you a Kruskals question on the exam and we just want the MST, you can do it without the union find, but it's good practice. So take a few minutes. I'm going to go AFK for just like 2 minutes here, let you work on this, and try to do the representatives also, and then we'll come back in a few minutes and do it together. Okay, I didn't actually go far, I just stretched a little bit. All right, so let's go through this solution. So we're going to start out, smallest edge weight is 1, 1 is in because it doesn't produce a cycle. So this edge is in. And then if we update representatives, we could say, okay, B, change your representative to be the same as A's representative. All right, there we go. So now we go to the next shortest edge, edge of length 2. D and E. Really, let's go through this in logically what happens in each step. We know DE is our next potential edge. We ask D, who's your representative? D says D. Because it said itself, we know it's correct. We know it's done. E says E. That one's done. Because they have different representatives, we know it is safe to join them. So we add the edge DE, which is a disjoint edge from the other one. And this is in, and we can say, oh, E changes its representative to be D. I always like to just change the second one to be the first one's representative. Whoops. So yeah, so D says D, E says E. We change E's representative to be D. Okay, so then the next one is AC. So we check AC. A's representative is A, C's representative is C. They are different representatives, so they can be joined. And C changes its representative to be A, and edge AC is in the graph. Oh, whoops, I'm one slide ahead of myself, or behind. So then we check AC. A says A, C says C. They're different, so that we can select that one. It becomes a real edge. C changes its representative to A. Now we're looking at the edge BC. We ask B, who's your representative? It says A, and then we don't stop there. B says A, we ask A, who's your representative? A says A, we know we're done. B's representative really is A. We ask C, who's your representative? A, we ask A. A says A, we know we're done with that representative. Since B and C both have the same representative, we cannot add that edge. We know that if they have the same representative, selecting that edge would produce a cycle. So union find does its own thing. Union find just keeps track of who is connected and who is not. When we say, I would like to do a union of B and C, and union says false, we say, oh, I don't add that edge to my selected edge list. I just skip over it. Let's go to the next one. So I go to the next one, CD. I ask C. C says A. We ask A says A. So C's representative really is A. D says itself. It's correct. It's whenever anyone says they're themselves, we know they're done. So C and A have different representatives, so they can be joined together. So we can choose the edge CD, and we'll change D's representative to be the same as C's representative. Now we check on the edge BD. So we ask B, who's your representative? A says A. We ask D, who's your representative? D says A says A. Because B and D have the same representative, we can't pick that edge. All right, moving along. Now we're pretending here we didn't stop when we had V-1 edges because I want to show you something. So we're looping until we've gone through every possible edge. Okay, we consider the edge BE. BE is the next edge in the sorted list, so we check the edge BE. We ask B, who's your representative? B says A, and A says A. So we know B's representative is A. When we ask E, who's your representative? E says D, D says A says A. So we know we've found the ultimate representative. E's ultimate representative is A, and we do path compression. Because E eventually found out when we asked E, who's your representative? E said D, D said A said A. As that recursion unrolls, everyone sets their predecessor equal to whoever the recursive call said their representative is. So E changes its representative to be A for path compression. Now we are finished asking. B says A, E says A. Because they both say A, we cannot do the union. We don't change anything in our list of edges in the MST, but the union find changed its internal data due to the path compression of vertex E. Okay, so there's our resulting graph. We'd say, hey, I've got a total edge weight of 11, and oh look, it's the same edges we found before when we did the Prim's algorithm on this graph. We found them in a different order, but we did find the same MST. Same total weight has to happen. The same edges happened to occur. Okay, so when we do this MST problem, the MST is the lowest cost subgraph that includes all the nodes. We've got to get all the vertices into the graph, and we keep them connected, and we want to find the minimum cost of edges that does it. The minimum cost will always be the same, even if we select different edges to get there. Now we've got two algorithms, Prim and Kruskal. They're both greedy. They're greedy in different ways. Prim iteratively adds the closest node that's not in the tree to the tree. Kruskal builds a forest by finding the minimum edge that doesn't produce a cycle. Now, Prim has to prevent cycles somehow. That's an important point. Now, let's talk about implementation. If we have a dense graph, we use the nested loop Prim. The theoretical complexity is the best, and it turns out to be a fast way to implement it. There are ways to improve upon it slightly, but this is sufficient to get you all the points on Project 4 or Part A. For a sparse graph, if we have a sparse graph, use Kruskal. Theoretically, the complexity of Prims with priority queues and Kruskal are the same theoretical complexity, but we've had multiple people on staff implement this. We've had people on staff implement this who were part of the ICPC, the International Collegiate Programming Challenge. Basically, people call it the ACM programming team. We've had multiple people on staff implement this both ways, and we've never had anyone's best priority queue Prim beat their first Kruskal. So if you do Kruskal right with the union find, no matter what you do to priority queue Prims, it never beats Kruskal in actual implementation. Theoretically, they are the same complexity. Implementation-wise, Kruskal wins. Now, something to think about is prove to yourself that Kruskal always finds an MST. Prove to yourself that it is minimal and that it is a tree. Prove that Prim. Prove that Prim always finds an MST. Think about how Prim can start at any vertex. And another question, like I just mentioned a minute ago, is think about how Prim prevents cycles. It's easy to see how Kruskal prevents cycles. We don't pick an edge that would produce a cycle. How does Prim prevent it from happening? It has to. It's in there somewhere. So think about how that occurs. Okay, so we're done with the lecture. I'll leave the video open for a minute or two and see if anybody has any final questions. And then I'll end the stream, and then I'll go and make the video. I'll make it added to the public section instead of unlisted. So if anyone has any questions, ask them. Otherwise, I will see you next week on Tuesday. You're welcome. It's unfortunate that I can't actually see you. I really do miss that. Okay, I hope this was helpful. It seemed pretty clear as we were going through. You're welcome, Carrie and Alex. All right, I'm going to end the stream since I don't want to cut off your thank yous. I love those too, but if we've got no questions, I'm going to end this and get some other stuff done. All right, take care, everyone. Good luck on finishing up the project.